So this paper titled Round and Round We Go, What Makes Rotary Positional Encodings Useful, it came out recently by Google DeepMind, and I think it is a cool paper because it actually tries to figure out what is going on behind the positional encodings in a transformer. That's something that we don't know that much about. So I think it's an interesting paper that it tries to explore that. And it finds some interesting insights, at least into the Gemma model. I don't know if this generalizes at all, but the findings they find are quite interesting, especially if it generalizes to other models, which I would imagine it would, because all the transformer models are basic, or they're based off the same thing, just the attention layer. So yeah, I'll briefly go over the rope positional embeddings, and but I made a video about that before, so I won't go too into detail behind that. But yeah, let's get started with rope. So the idea behind rope is, well, at least the intuition that was initially thought of behind rope is we have some set of tokens here. So we have some set of tokens, and whenever we have our attention matrix here, let's say, what is this, 5 tokens? This is a 5 by 5 matrix, and you basically have your, we'll make it causal, make it easy. You basically have your attention here, and the first way they made positional encodings was just by saying, oh, this is token 1, this is token 2, this is token 3, this is token 4, this is token 5. And that was done using the sinusoidal positional embeddings, when those were just absolute positional embeddings, just saying where is each token with respect to the start of the sequence. Then rotary positional embeddings came around, which the idea was basically how far is a token away from the token being attended to. So for this token here, let's go with, let me draw it out. 1, 2, 3, 4, 1, 2, 3, 4, and there. All right. There. So that's a terrible mask, whatever. So this first row corresponds to the first output. So this is just the token itself. So position 1. And let's define this diagonal as basically position 1. Then the idea is you define these positions relative to the token being attended to. So for token 2, you have token 1 attending to token 2, and the relative position would be, I don't know, something, it wouldn't be a 2, but it would be something similar to that. Some way indicating this is 1 token away, and then this would be 2 tokens away. The first token would be 2 tokens away from the third token, and so on. So these are the relative positional encodings. And the idea behind rope was basically you have this decay where you have your first token, or closer to that token, there's more attention, while further away from that token, there's less attention. At least that's the idea behind rotary positional embeddings. At least that was one of the reasons people thought it worked. However, they actually show in this paper that that's not true at all. Anyways, so rotary positional embeddings, how do they work? So sinusoidal was just adding sinusoid, or like sine and cosine to here, to each dimension in your vector, to your d-dimensional vector. Rotary positional embeddings basically says, all right, so we have a vector here. This vector is d-dimensional, and what we're going to do is we're going to rotate it. So in the simplest case, let's say d is equal to 2. Then we can define a rotation matrix. They call it, I think it's just rho, of gk is equal to the rotation matrix gk, sine of gk, negative sine of gk, and cosine of gk. So gk is just the angle. So the idea is you just rotate a 2-dimensional vector some amount. So, I mean, you could think of this in terms of like theta. So you just rotate it some amount, and that's it. And you do that via this matrix here. So each g represents radians. So yeah, this is a rotation by radians here. And what you do with positional or rotary positional embeddings is you define this theta parameter here. And this theta parameter basically, well, in this case, they use theta. So theta is going to be defined as basically the frequency we're going to use. So in the original paper, they used 10,000, and what we're going to do is we're going to basically assign a value of theta for each pair of dimensions here, and we're going to rotate each pair according to that frequency. So d is maybe like 128 or something like that, and we're going to basically split this into pairs of dimensions. So this one would be d is equal the first dimension and the second dimension. This pair would be the third dimension and the fourth dimension, and so on, just for each pair. So if d is equal to 128, then we would basically have two vectors where d is equal to 64. Or you can think, 64 versions of vectors of 2, 64 pairs of vectors. And we're going to rotate each of these independently from each other, just using this matrix here. So if we have a vector with 128, we would basically take the first pair, and this would be one vector we're going to rotate. This is the second pair we're going to rotate. This is the third pair we're going to rotate. And we're going to rotate them according to this theta value. So for the first dimension, we're going to assign theta is equal to, or it's going to be these g values, the radians, which are a parameter of theta. So this first one is going to be g is equal to, and in this case, it'll be theta to the power of 0, so this would just be 1. And in the second, for the second set, we're going to define a value, a negative value up here. So it'll be negative some decimal, I don't know, maybe 0.1 or something like that. And you're going to do that until you get to your last dimension here, and this will give you a g, which is equal to theta to the negative 1. So this would be 1 over 10,000. So what you do is you define these rotation matrices, which are rotating the dimensions independently based off these pairs. And you're going to have different frequencies for each pair. And the first frequency is going to be 1, so it'll be a very high frequency. This is basically rotating by 1 radian, so you get quite a bit of rotation. The initial vector is not going to be that close to the new vector after rotating by 1 radian is not going to be that close to the initial vector. And you have 1 over 10,000, which is basically no rotation at all. You rotate by 1 over 10,000 radians, that's like no rotation. So this is what you do. They spell it out better over here. Basically, you're going to define this R matrix, and this R matrix is just going to be a big matrix that looks like this. It's a diagonal matrix, which is a D by D matrix, and you're going to use this to rotate every vector. So D by D matrix, use that to rotate every vector. And what you're going to do is you're going to define R to the power of I, where I is the ith index in the sequence. So I would be equal to, say, 1 for the first vector in the sequence. So whatever the first word is, this would I to the power of 2 for the second token, I to the power of 3 for the third token. And basically this defines a rotation. So I to the power 1, that's going to be 1 rotation by this matrix. R to the power 2 would be 2 rotations, and so on. And basically what this is doing is saying if we have, I don't know, say 3 tokens here. So we're going to rotate this token 3 times and this token 3 times. And the idea is that since the rotations are the same, relative to each other, it'll be like they didn't rotate at all. But relative to the other tokens, there will be some rotation according to the frequency defined by the theta parameters for every dimension that shows that this is 1 rotation matrix away from this one, and this is 2, and so on. So that's the idea, and over here, they basically show you rotate your queries and your keys using the same rotation matrix, and this defines this relative similarity, where since whenever the powers match up, you get this, or rather combining R here gives you this matrix here, which is just a matrix basically in between this inner product here that you're defining. And whenever I and j are equal, this is just the identity matrix here. So there is no rotation at all relative to each other. So, but whenever I is not equal to j, you get this relative rotation using this power of your rotation matrix that you're multiplying by on the pairs of dimensions. So that's the idea behind that. So a couple things to mention. They mention that 500,000 is good, is a better base than 10,000. We'll get to why that is, but it was something that hasn't really been explored much until this paper. But 500,000 is somewhat better for some reason. Another thing to note is that there is this, I do not know where they define it at. Maybe down here. Yeah, nope. There's this positional embedding scheme called nope, which is no positional embeddings at all. At least that is what I am led to believe. Nope. And basically this just doesn't do anything. So it's kind of a basis saying if we apply no positional embeddings, so nope, does the model do as well as if we had rope? And if it does, then does that mean we don't need positional embeddings at all? And they basically show that rope has some interesting properties that nope does not. And since we're doing causal attention, the model still learns positional, positions of the tokens via the causal mask. So it can still learn positions. So that's why nope can be used, but you're not directly adding these positional embeddings. So is rope actually beneficial? So the first thing they look at is, does rope decay activations with distance? This is basically one of the biggest claims with rope is that, or this is one of the explanations for rope, is that it decays as distance increases from a token. So you have your attention scores for some token. It's very high whenever it's close, and it's low whenever it's far. And they show that this is not the case. So the way they do that is they say, all right, so let's look at these queries and keys. And typically, I think typically what they do is they assume that the queries and the keys are equal. And if you do that, they say all ones for the queries and the keys. And you look at the relative distances, you get this decay here. So relative distance, this would be the same token. This would be a token really far away from a token. And you see that the activation does indeed decay. This is the logit before softmax. However, if you use Gaussian queries and keys, then you find that rope doesn't do anything. Or rope doesn't have this decay, rather. So if you use Gaussian queries and keys, you don't find this pattern. And I don't know, you pick one assumption, either are they all equivalent or are they Gaussian? Gaussian is probably a better assumption than having the same queries and keys. So I would lean towards this argument here, where the distance doesn't matter, but I don't know, pick an assumption and go with it. But if you assume Gaussian, then you don't have this decay. So yeah, that's basically the argument here. But basically they're showing that this argument of it having this decay is probably not true. So yeah, that's that part here. That one's pretty simple. The next part is how are the different frequencies used? So getting more into what is going on here. They basically look at, this is the mean distribution of the magnitudes over each layer. So they mention this here. Basically, we want to look at the dot products of, along the dimension. So dot products are the inner product of the queries and the keys, and specifically on the kth frequency. And they mention that this is bounded by the individual magnitudes, and this is just the Cauchy-Schwarz theorem. Basically, for the kth frequency, the inner product is bounded by the individual inner products. So they look at the individual inner products on the queries and the keys, or the individual magnitudes of the queries and the keys. The inner product, the magnitude of the inner product is bounded by the magnitude of the individual vectors. So we look at that. These are the queries. This is the average magnitude for, this is an average magnitude over layers and over the dimension. So they look at the low frequencies and the high frequencies. This is just our dimension here. And this is every layer in the GEMMA model, or every other layer in the GEMMA model. And this is what they notice. They notice that there are the frequencies that are used most are these low frequencies here for almost every layer. And none of the high frequencies are used. So this would be like a radian, or this would be like theta is g is equal to 1, and this would be like g is equal to 1 over 10,000. So the values down here are used much more than the values up here for both the queries and the keys. But they show that in some cases, these high frequencies are used. Even though the low frequencies are usually mostly used, there are some attention heads where this is not true. So this is just looking at the individual heads instead of looking at the individual layers. And they show that there are some heads, they look at 5 and 8 specifically, because these have the most interesting patterns for both the queries and the keys. They look at these two heads, but they mention that some of them have this weird high frequency usage, while mostly low frequencies are used. So mostly low frequencies are used, but sometimes high frequencies are used. And let's get into why that is. So first off, high frequencies. High frequencies are these are very, very fast rotating vectors. So if I have a vector that is, say, here, and I have one that is just one position away, the rotation will be, well, maybe not orthogonal, but the rotation will be quite high. And 2 positions will be like that, and so on. So the rotation is very, very high for these high frequency positional attention, or for these high frequency dimensions. So they look at the high frequency attention heads here, and they see that, so these are this is attention head, head 8, layer 27. They basically look at the heads where there is a ton of, the magnitude is very, very high for the high frequencies, because typically it's really low. So they look at the ones where it's very, very high for the high frequencies, and they find these interesting patterns here. Here's one of them. Basically, this is just a diagonal attention pattern, and this is just an identity, essentially, here. And they also find this one here, which is copying the previous token. So the current token basically just becomes the previous token. And they mention that they look at a lot of these heads, and they see very similar patterns. And they mention that the high frequencies are used just for positional information. And that's because of this high rotation here. If you have a vector here, so this is, I don't know, maybe word I in the sequence, then word I minus 1 is going to be very, very different than word I with very little, and it doesn't even have to be that far away. And the next vectors will also have that property. And it'll take a while. It'll take a lot of rotations for a vector to be similar to vector I. So this is basically the argument behind this. It's saying, since you have these very, very fast rotating vectors, they're going to be very dissimilar to vector I because of that. And this basically doesn't allow you to store any information about the vector I at all. But what it does allow you to do is it allows you to store information about the position, or rather use information about the position, because all information about the vector I is just thrown away because it's rotated so much. So basically they say these are positional heads. These heads are used for positional attention here, like as shown here. Basically, it learns these positions here. It doesn't learn anything about the semantics behind the token. It just learns, this is how, I don't know, you just pass tokens to the next. This is like a residual connection here. This is how you just copy the previous token, but it doesn't do any attention here. It doesn't really do anything with the semantics of the tokens. It's just purely positional because it only has positional information to work with along this high rotating, or this very, very fast rotating frequency. Yeah, so that's that one. And they show that Nope cannot learn this. And that makes sense because Nope is not, there are no positional embeddings. It can't learn this relative, this relative position. Rope can, like as was just mentioned, but Nope cannot. And they show a proof below. I think the proofs are kind of interesting. I think for this one, they assumed two vectors were equal. So I don't know how well that holds. But nonetheless, it makes a lot of sense that Nope cannot learn this. These purely positional heads up here. So one benefit of Rope that Nope may not have. So high frequencies learn positions, but they cannot use semantics at all. Low frequencies are basically purely semantic. So if we look at a low frequency vector, or a low frequency rotation, basically I have a vector here. This is vector I. And let's say I have the same vector, then vector, let's say I rotate it by, 1/10,000 radians. Then vector I is basically just vector I again. So it doesn't move like at all. So it's very, very slow at moving. And since it's very, very slow at moving, you basically don't use positions at all in these very low frequency cases. So down here, low frequency cases, you don't use position much. You basically only have semantics of the token because it doesn't rotate much. And if you have a dot product between two vectors where the rotation isn't much, then you basically just have the dot product between the two vectors. And intuitively, this should make a lot of sense. If it doesn't rotate much, then it only is using the semantics. And this explains, or it has a pretty good explanation for why 1/500,000 works better than the default 1/10,000. Oh, I need to charge my tablet. It'll be fine. It won't die. So yeah, 1/500,000 is better than 1/10,000, which is used in like Llama 3. And that makes a lot of sense because the rotation is a lot less. So instead of using instead of rotating at all, you rotate a lot less. And basically it just allows it to use the semantics a lot more than the position itself, which is just a small rotation. Now, let's say we have a lot of tokens. Let's say we have a ton of tokens. This argument doesn't hold where the rotation doesn't happen at all. If I have a lot of tokens and I am basically rotating them by maybe not 1/10,000, but something smaller than that. Maybe it's not this bottom frequency that we were looking at, but maybe it's a little bit higher. So it's some rotation that's not 1/10,000, but some rotation that as you rotate this vector, so as the power of r increases our rotation, you start to rotate this vector in a significant way. So if we rotate it maybe 4 or 5 times, it doesn't rotate at all. But let's say we rotate it 1,000 times, maybe it does change a little bit, and it does change significantly. And this kind of explains why the models aren't very good at extrapolating that much. At least I think so. Basically, you have a model that is only using the semantics of these vectors here because there is no rotation. However, if you keep increasing the sequence length more and more, then you're going to end up rotating these vectors in a significant way because of that, because you're just rotating by a small amount every time, and they will eventually add up to some rotation. And this, since it's basically only learned how to use the semantics of these vectors, it doesn't know, like, this vector now has this position that is, it's weird. It basically changed, they would interpret this as the semantics of the vector, which have changed, but that's just due to the rotation. So you get, since it's rotating after so long, I think that's why the extrapolation isn't that good. You basically get this rotation. It's like, I haven't seen that before in this position. That's kind of strange. I don't know why it's rotated. It shouldn't be rotated here. And then that's whenever you get probably these weird this behavior in the model where it just dies after some amount of time, or after some number of tokens, because it rotates when it shouldn't be rotating. So they mention down here, they say that with a context length of 128,000 in Llama 3, the standard wavelength of 10,000 will complete within 2 rotations. So that leads to problems. So poor generalization due to tokens being misaligned simply due to the large context. So large context can cause problems because even with this small rotation, because the vectors only uses semantic information the models only use semantic information at low rotations. Now, and that's why 1 over 500,000 probably works better, because you rotate the vector a lot less than if you had 1 over 10,000. So you can probably extrapolate further because you change the space, and the frequency makes it rotate a lot less. So you can increase the number of tokens you have, and it'll still retain the semantic information. It'll rotate a lot less. So this is basically the argument behind low frequencies. It's only using semantics because the rotations are very small. In some cases, you get some interesting mixes here. So this is a semantic apostrophe attention head. That's what they mention, or that's what they name it. And basically what this does is every time it finds an apostrophe, so at 3, 9, 15, it attends to the previous token. So this requires you to use position and also semantics. So basically you get these high frequencies for the apostrophe token. So this would be using some positional information, and it still uses these low frequencies for kind of the semantics. But yeah, you get these mixes as well. But yeah, these are kind of the arguments that they're making. Basically, high frequency position, low frequency semantics. And they say that what you can do is after making these arguments, they say, well, one idea is, since you run into these problems with these low frequency rotations, rotating after some amount of time, what if we just truncate those to 0? And then you don't run into this problem. So truncating the low frequencies of rope, basically all they do is they define this p-value. P is just some cutoff value, some percentage. I think they define p is equal to 0.25 and 0.75. So 75% will be cut off, or is that kept? It is, okay, 75% will be kept and 25% will be kept. So this is the percentage that you keep, p. So they define p rope here, and this is basically 25% of the frequencies are being kept. So this will be so we have our d-dimensional vector. Basically, these frequencies, the high frequencies, the top 25% of the frequencies will be kept, while these will all become 0 for our rotation. And for this, it'll be 75%, so you keep more. And they basically only test on 2 datasets, and they show it's better. They don't really show anything more interesting than that. They only do 2 datasets, and they say it is better in terms of perplexity. I don't think these results are interesting at all. I am curious to see if this extrapolates better, because the main reason you would want to cut off this frequency is to see if these rotations, since you're not rotating this vector at all anymore, see if it extrapolates any more than it does, since the extrapolation problem, or at least part of it, may come from this rotation after a really long sequence length. Does this fix it? Does it at least make it better? Like, the perplexity is a little bit lower, but it's like, it's not that much lower. It's just slightly lower than rope. But what would be interesting to see is if this extrapolates better or not. But yeah, basically they define p-rope, which is a little bit better, and it's just assigning 0 values to the low frequencies so that it doesn't have this rotation issue. And it just uses semantics instead. All right, so that's the paper. Now, one thing I want to just talk about, so I don't know if this exists at all, but why not just define something that learns the frequencies? So we have a vector over here. I need to scroll up to it. Yeah, so this here, R. Why not just define something that basically learns the basis, or rather the G values here? I don't know. Why not make this learnable? And what would be interesting is if you make this learnable and then you look at the frequencies it uses, because in this paper it's basically arguing that low frequencies and high frequencies are important. High frequencies are important for position, low frequencies are important for semantics, but what if you have GB learnable? I don't know if a paper exists out there that does that, but have GB learnable, see what frequencies it wants to learn, and see if it learns low frequencies or higher frequencies, what does it end up with? I think that would be interesting. And if paper does, look at the frequencies and see if see what it learns. Does it learn low frequencies? Does it learn high frequencies? Because this basically just defines just all the frequencies from radians equal to 1 to not 0, but 1 over 10,000. So yeah. But anyways, that's a paper. I think it's interesting that the rotary positional embeddings give you these cool properties of either learning position or learning semantics based off what the frequency is. But yeah, I think this is a cool paper. It's going in the direction of trying to figure out what the heck transformers are actually doing. There aren't a lot of papers on that right now. But yeah, cool paper nonetheless. Let's see if this kind of goes anywhere.